All right, here's the problem. We're given a collection of stones and we're just gonna and these stones have a weight. So 2 is a stone of weight 2. And then what we're gonna do is we're just gonna pick up the 2 heaviest stones and smash them together. And what happens when we smash them together? Well, if they're the same weight, they both perish. They're just both gone. If one is bigger than the other, then the smaller one will perish, but the big one will get chipped. So in this case, if we try and smash 7 and 8 together, the 7 will just be gone, but the 8 will get chipped back into 1, and then we, put it back into our collection of stones. And then what they want to know is at the end, if we smash 2 stones with the same weight, we'll get 0 stones left, or we're going to get a single winner, our 1 stone left. Okay. So they give us a nice constraint. We'll never get more than 30 stones, and each stone weight will be at most 1,000. So our goal, I guess, is to first, find the 2 biggest stones. Now, how are we going to do that? We can actually use the constraint to our benefit, and we can make something called buckets. So what here is our buckets. And what buckets are is it's going to keep track of how many stones we have of the weight of that bucket. So in this case, this is a bucket of 0. So this is going to contain all the stones I have of weight 0, which is none. Here is my bucket of 1. So in this case, we have 1 and 1 here. So we'll have, 2 stones here at this bucket. 2 gets 1 stone. And then we have 4 here, 7, and 8. So when we're reading this bucket, I could have read from left to right. So 2 here, drop a 7 there, drop a 4. And now what that gives us is if we were to iterate in this direction, we can always get the 2 biggest stones fairly easily. So that's how I want to process my stones. I don't want to process them in the original array. I want to create a bucket out of them. Now, the reason we can do these buckets is because we're guaranteed that our max weight is 1,000. So at most, we'll have 1,000 buckets, which is not bad. Although we could find, for example, 8 is our max here, and we just create, 8 plus 1 buckets. So here we have 9 buckets. Cool. And we also know there's going to be at most 30 stones. So at most, in a single bucket, we're going to have, so the distance from here to here is going to be 0 to at most 30. Okay. So let's try creating our buckets. What I'll do is let's find the max weight first. So we have a max weight of, I guess, stones at 0. And if our stones.length is less than 1, then we'll just return 0. So we don't even have a stone. So the last stone weight is 0. Okay. Now we go through each of our stones. And if stone has heavier than our max weight, then max weight is equal to our stone. Okay, so with that we have our max weight, and now we want to create our buckets. So I'm going to create a byte array of buckets. Now the reason I choose byte is because if you look it up, so byte primitive Java, byte only holds 8 bits. So here, and it has a minimum of -128, maximum of 127, which is good because at most we'll only get 30 stones in a bucket. And because we might be potentially making a large array of, because we need a bucket to hold our 1,000 weight stones, having a byte array instead of an int array will actually help save us memory. So here we're going to use our byte array of buckets. And we're going to we need to hold the weight of the maximum weight. and plus 1 because this will give us 0 bucket all the way to max weight bucket inclusive. Okay, so let's fill up our bucket. So we'll read over again. And our buckets at this weight, we're gonna give it our stone. Cool. So now we have our buckets. Nice. Okay. So our next step is we want to find the big stone. So what is our big stone gonna be? I don't really know, so I'll put -1 for now. And it seems like our big stone is we just want to iterate from the rightmost side, right? So for maybe something like int I equals 0 or max weight dot length -1, I greater than or equal to 0, I minus. And if our bucket at I is greater than 0, then our big stone is equal to this weight, right? Okay. So, what we're doing here is we're scanning from the left side and we're saying if I see a non-empty bucket, so for example 8 here, then this will be my big stone. Now, something we have to notice here is that we can actually make an optimization here. So imagine you have a bucket with 4 stones. What's going to happen of the same weight? What's going to happen is that these two are going to smash into each other and they're going to disappear. These two are going to smash into each other and they're going to disappear. And what happens is this means that this bucket, we don't actually need to take a stone from it because we know already that all the stones will be used. Now, what if there was a 5th stone? Then you can see that now we have an odd number of stones, and really we just pick this single stone and we can continue on. So we never have to actually do like our simulation of smashing stones for each stone, because we know even number, they're all gone. Odd number, there's only this one left, and this is what we'll pick up as our big stone. So instead of this, what we can do is let's create a new function. We'll call it find our odd bucket, because if it's an even bucket, so a bucket with even number of stones, we can just skip it because it's not very useful for us. It'll take our buckets and it will also take where to start searching from in our bucket. And then what we'll have is, I guess, while I is greater than or equal to 0. Let's see, we want to say here if is even, then if it's odd, then we return. So what we can do is if buckets at I 1 equals 1, then we return I. Otherwise, we continue on the search. Okay, so if you haven't seen this before, what this does is it calculates whether or not this is our buckets at I is even or odd. So very briefly, what it does is, let's say you have a number, for example, 3 in binary. So this is 3 in binary, and what it does is it ANDs it with 1. So an AND, it will only output 1 if this is 1. If this is 1 and this is 1, then it'll output 1. So here it's 1, but if this happens to be, if it's another number, say 4, this is 4 in binary, then what will happen is that our answer is going to be 0. So basically, this AND 1 operation tells us, if it's equal to 1, then it's odd. If it's equal to 0, then it's even. And it's just a fast way of checking for even-odd parity. Okay, so here's our AND 1 equals 1. So if it's odd, we return the one that we found. Otherwise, we continue on our search. So now we can say, in our big stone, we're going to find our odd bucket using buckets and add some integer I. So for now, let us just put, I guess, we'll start from the end. So it'll be buckets.length -1. And that should give us what we want. Oh, right. So what happens if we don't find this odd bucket? Well, we'll just return 0. So here what we can actually do is we can, while I is greater than 0, and then here it can return I. So what happens is we'll do I minus minus. So here it'll be 1 greater than 0, and then 1 minus minus is 0, and then we'll exit out, and then here return I will be 0. And so that means here we can actually do, I guess, break instead, and then we can always return I. Cool. So here is our big stone. We have our big stone. I guess now we have to check if big stone is equal to 0. So we couldn't find a big stone. Then we are done. That means the last iteration we smashed 2 rocks together, and then we couldn't find another rock. So, if there's no more rocks, we return 0. Okay, so now we have to find the smaller stone, which could be just as big as the big stone, but we'll call small stone. Or I guess next stone is more appropriate. So the next stone to use, we want to, so we know that the big stone, in the big stone, after we found it, the smaller stone must be on this side, right? Because we're either going to skip it because we used up all the stones, or we're going to pick up the biggest stone, so then that one's used up. So our next stone is somewhere along this side. Okay, so we, instead of finding an odd bucket, because we have to actually pick the next stone, we will just create another helper function, and this one will be pick next stone. Again with our buckets, intet I, and then here we'll have for, I guess, I greater than 0, or greater than equal to 0, I minus minus. If buckets at I is greater than 0, then we're going to pick it. So how we pick it is we're going to decrement it, right? So we pick a stone. So that decrementing literally means, if we have 1, 2, then when we decrement it, we're here, we'll just decrement it by 1. So it's like we picked it out of the pile. Okay, so we picked it out of the pile, and we can break here, and here we can return I. And again, I guess we want to do I greater than 0 because we don't actually want to search the 0th bucket. That way we return 0 here. Cool. And I guess to make this the same, we can do the same thing here. I minus minus. If our bucket is even, break, and the I minus minus, return I. Okay, now they're pretty similar, except this one finds an odd bucket, while this one just finds any bucket with stones in it, and we'll just pick the next stone out of it. Cool. Okay, so here's our next stone. So our next stone, we're going to pick, I guess, next stone with buckets, and then we're going to start searching from where our big stone was, -1. Now this, as we see, will have an optimization later, but for now, this makes sense. We're going to pick from the next stone. Okay, so with those two, we're going to smash it together. So we're going to have a new stone, I guess, which is going to be equal to a big stone minus next stone. Now there's a couple of cases that could happen here, so let's explore them. So in the first case, if this is our big stone, so we're coming in and we find, an odd bucket, So this is our big stone. And then we ask it, okay, start finding the next stone. So this will be empty. And then here we find our next stone. And then what we do is we want to smash these two stones together. So let's give them some numbers. Maybe this is 1, 2, 8, 6. When we smash 2 and 8 together, we're going to get a stone of size 6. So we're going to get a stone of size 6, and these two are out of the picture. Now what we notice here is that this is our next big stone, and our next stone is actually still going to be somewhere in here. So we don't need to search this area anymore. We don't need to search big minus 1 because we already searched all the way to 2. It's just that we know that our big stone is going to be the result of the collision. Okay, so we have another case here that is slightly different, where we have two big stones that are going to crash into each other. So here, this is our big, and this is our next. And again, we'll give them some numbers. And then what happens is we pick up the big stone and the next stone, and we smash them together. So these two are out of the picture, but they're going to create a new small stone at 1. So that means we have to increment here. We have to increment our bucket here that we created a new stone. And then we need to continue searching on from here because, I forgot. Because there might be a stone here that we haven't seen yet. So we can't just assume that our next stone is going to start from wherever the smash happened. It has to start searching from here, going all the way down. So these are the two cases that we should watch out for. Okay, so let's see how that plays out. So we have our new stone, and now if this new stone is greater than our next stone, then we know that our big stone is actually equal to our new stone. So this is the first case where we had the 8 minus 2 equals 6. So we found our next big stone for free. Otherwise, in our buckets, at our new stone, we're going to increment it by 1 because we found a new stone of that weight. And then now we actually need some sort of way to know if we already found the big stone before. So what we can do is we can set the big stone's weight to -1, and you can have a guard here saying, we'll have int big stone equals -1, and if big stone equals -1, then big stone, we have to find the next big stone basically. So that'll help us, because here we already found the next big stone, so we don't need to do it. So, I'm imagining this is probably some sort of while true loop that we're doing here. And we'll have all of that indented, like so. Okay. Oh, we almost forgot. So what happens if we don't find the next stone? So here we're trying to find the next stone, but we go all the way down to 0, and we never found the next stone. So here we actually need to add if next stone is equal to 0, then we return the big stone. And that makes sense because by here we're guaranteed that we found a big stone, because if we didn't, we would have returned 0 earlier on. Okay. So in big stone minus next stone, and we get a new stone. And if our new stone is bigger, then we have our new big stone. Otherwise, buckets, new stone plus plus, big stone minus 1. Okay, so let's look into a little bit. The last thing that we want to look at is these ones, because this isn't quite correct yet. Okay, so when we try and find our next big stone, we want to actually start our search by wherever our next stone ended up. In other words, let's say in this picture, right? So we need to find our new big stone. Let's see. And we knew that if I just revert what it was before, we had this where we knew that the next stone was here. And then we picked these two up and smashed it. And then we had this stone come in. Now, where do we start searching from? We're going to start searching from where the next stone was. Because remember, the next stone, we could have had multiple stones here. So it could have been something like this. And then we picked up big stone and next stone, and we smashed it. So we want to actually start our search from here, because there could still be stones in this bucket. So what we want to do is we want to start our search from the weight of the next stone. So now we need next stone is equal to buckets.length minus 1 to start off with. And here, okay. So if we find a big stone, then we know that next stone, it should be big stone minus 1. But remember how there was that case where we got a big stone for free? So in this case, we got our big stone for free. So we could have, so this is let's see. We got our big stone for free, so we don't actually need to search here again. We can search from wherever a new stone was previously. So here we want to set this to actually be next stone. So just search from where you were searching before, and we'll find the next one. And then here what we want to do is we want to say next stone is equal to big stone minus 1. So if we did have to find a new big stone, then we need to start searching from, the next available bucket, because the big stone is going to use up the whole bucket, because it's either an even bucket in which we skip, and if it's an odd bucket, it's going to take the only odd stone there is. Okay, so that should give us what we want, and we have our two exit conditions of either we return the big stone or we return 0 if we can't find a stone. All right, let's give this one a run. Make sure that it compiles. Okay, looks like it compiles, and we'll submit. Ooh, runtime error. That's not good. So line 35, let's see where we did. Line 35, where we picked up a new stone, and it said it's index out of bounds, and it looks like it's an overflow. So some sort of overflow happened. Let's see. Big stone minus next stone. That's correct. And otherwise, buckets at our new stone plus plus. Maybe we did this one correctly. Let's see. Buckets at I, it's even, then, oh, I see what we did. We didn't need this I minus minus. Right. Because we converted it from a while loop that had an explicit I minus minus into a for loop that had it in here. All right. So here is our new one. Looks like it compiles. We'll try submitting again. Okay, cool. Now this time it's accepted, and it beats 100% of the runtime. All right. So Sorry about that last mistake, but that's it for today. See you on the next day.